The overall goals of this lab were to first create a computational model that showed the charge evenly distributed across the tape, and second, compare the results of the model that treated the tape as a point charge and the model that treated the tape as a line charge. There were several fundamental principles being used. First, the concept of net force was used, whereas the only forces we are looking at are gravitational force and electric force. Since net force is zero in this experiment, Fg is equal to Fe. We also looked at the concept that gravitational force was equal to mass times gravity. We also looked at the formula for Coulomb's law and the formula for calculating the E field of a uniformly charged rod. Finally, we also look at superposition. Here is a summary of the results from Lab 1. We can see that the magnitudes of gravitational and electric force are equal to 0.001991 newtons, and the charge acting on the tape is 1.79 e to the negative 8 coulombs. In the force diagram, you see the forces acting on the tape, which is treated as a point charge. There were several assumptions that had to be made before beginning the Lab 2 code. First, we had to assume air resistance was negligible. Second, we had to assume each piece of tape had the same charge and uniform charge density. Once we made these assumptions, we could begin to estimate Q. By treating the tape as a series of point charges with uniform charge density, the formula for a uniformly charged rod could be used to get a starting estimate of Q, as seen in the work on the right. Once the code ran, I used guess and check to get the exact value of Q that yielded an electric and gravitational force that were of equal magnitude. Next, we needed a function to calculate electric force. This code was taken from Lab 0. Then, we needed to edit the position vectors for the tapes. This data was taken from the experimental results of Lab 1. Next, since we were treating the pieces of tape as a series of point charges, we could calculate multiple electric field vectors for each point charge. Finally, the net electric force vector and the gravitational force vector was created. The image on the right is the final result of the code when ran. The final Q value that was found after a few rounds of guess and check was 1.05135 e to the negative 8 coulombs, while the magnitudes of the gravitational and electric forces were 1.993 e to the negative 3 newtons. The diagram on the right shows two lines of point charges, with multiple arrows representing the electric fields of the point charges, and two arrows representing the gravitational force and net electric force. This is the expected result. When we compare the results from Labs 1 and 2, we see that the magnitudes of charge were slightly different. This is because Lab 1 treats the tapes as a single point charge, while Lab 2 treats the tapes as a series of point charges. The results from Lab 2 are more accurate because the charge on a long piece of tape is going to be distributed along the tape, as seen in the Lab 2 model. When we look at the percent difference from the charge found in Lab 1, which uses the point charge model, to the charge found in Lab 2, which uses the line charge model, we see there is a 52.1% difference. These values differ because the point charge model shows all of the charge concentrated in one place, while the line charge model shows the charge evenly distributed across the tape. We know that the line charge model from Lab 2 is more likely to be closer to the real value, because charge on tape is not concentrated in one place. Rather, it is distributed across the entire tape. In conclusion, we used GlowScript code to model a system of two charged pieces of tape, with the charge uniformly distributed across the entire tape. We found the charge on the tape by first estimating the value using the equation for a uniformly charged rod, then by guess and check. Finally, the results from the point charge model and the line charge model were compared.